So last time we were trying to finish the proof. So let's see where we were. Okay, so I guess you would remember the procedure that we had written for A prime, B prime, C prime, right? So we had this. So this is just quick recall. So we had this construction for construction of, depending on ABC, right? Where ABC was breaking the decision version, and we wanted to extract S, right? So we call this was breaking the decision version, breaking hybrid 2. Okay, and this we want to break the monogamy of entanglement or the strong direct product, whatever. So it's basically extracting SS prime. This is what we want to do here. Right, so this is where we were. Is this thing on? Check. Yeah, okay, good. 23 should be fine. It'll take a minute, I guess. Okay, so this is what we were doing, and the construction was. So we had written the construction for A prime as follows, right? That it got the coset state, right? And A would send delta. You sample 0, 1 and lambda. H is your random oracle, and you were using HSS prime, which was replace with U at SS prime. Okay, otherwise H. So that was the construction, and you simulated access to HSS prime, right? And this it could do because it got access. So everyone has, so they get access to PA plus S and PA perp plus S prime. So these are membership checking oracles, right? Everyone had access to these. And then this would send basically, so the BC states that it's going to send are the states that are produced by A, right? So A sends delta in the original game. You simulate the random oracle yourself, and at SS prime you produce a random U, and then whatever BC you get, A prime is going to forward it, and then they're going to run B prime and C prime, and these are supposed to output SS prime, so SB, SB prime, and this outputs SC, SC prime, right? This is what we had, and then we had some construction for B prime and C prime. So this is where things got a bit more interesting. So to define B prime, so remember we first defined pi 0b and pi 1b, right? Which was that you run B as it is with the appropriate oracle, you make a measurement, you run it backwards, yeah? Okay, and then the action of B prime was as follows. So B prime would so apply this measurement, this symmetric, I guess, threshold something. I don't know what the abbreviation stands for. The paper doesn't specify, but we saw this in theorem 2.8, right? I wrote down I didn't write the symmetric version, but the symmetric version was fine. And we used these parameters. So we used P to be pi 0b plus pi 1b by 2. Okay, and remember that in the construction, in the theorem, we wanted P to be a sum of projectors. Okay, so this is indeed a sum of projectors. Q is identity minus P, gamma was 3 by 4P, epsilon is whatever, 1 by 4P, and delta was 2 to the minus lambda. Okay, so but the crucial point was that after this, if the outcome is 1, So B prime is now going to runs B with 80H1 picked at random. Okay, and then B prime measures and outputs a random query to B, a random query made by B. Okay, and you do essentially the same thing for C prime. So this was the thing that we had managed to write last time, and we had to argue that indeed you are able to output, you know, whatever this output is, that these are actually going to correspond to the correct SS prime. Right? This is the main thing that we had to prove, and we ran out of time last time, so let's finish that. Okay, and yeah, maybe I can write C prime is similar. So C prime is analogous. Okay, so okay. So the story is that we want to, so given this A prime, B prime, C prime, want to argue that if W is non-negligible, it implies A prime, B prime, C prime. Yeah, basically remove the first line. Okay, so we just want to argue that if W is non-negligible, then A prime, B prime, C prime outputs SS prime. Okay, and W, remember, was the weight that we were trying to show in the characterization of the state, right? Okay, so let's do this now. So the first observation now is that from theorem 2.8, the first point. Okay, what was the first point? I don't actually remember. Give me a second. I think it's good to actually write down the first point, otherwise it would just look mysterious for no reason. Okay, so the first point is this is better. So point 1, so this is basically just a quick reminder. This is saying that the probability of measuring 1 on both registers satisfies, so we had, you know, the measurement that we had for the, so I'm not going to write the whole thing, so I'll just write 1. 1 is the first one, the first system. ATI2 is the second one, right, on row, is the same as trace. You make the threshold measurement, you know, which is projecting on the correct eigenspace, tensor E on the second eigenspace, row 2. Okay, so this trace minus 2 delta. Okay, this is the first point. Okay, so this is what we're going to use. That's the first point. Okay. And we're going to use the observation that, you know, conditioned on W being greater than 1 by Q, which was in the premise, right? It follows that both B prime and C prime get outcome 1 with probability Okay, yeah. So given this, what should the answer be here? With what probability? So what was W? It's not on the board, we did it last time. So W was the weight, right, on both being higher than, so we had the characterization of the state, right? So we wrote psi was some over alpha j, and then there were some eigenvalues here, right? And we said that is the projection where these eigenvalues are, like there was psi and phi, right? I forget what notation we used, right? And then these two were both corresponding to the eigenvalues being greater than a certain value, which is essentially the state want, right? That's what the, so if you look at the theorem was saying what? That you have these efficient measurements, and the probability that both efficient measurements output 1 was essentially the same as the original state has eigenvalues greater than some threshold, right, minus some small fact. Okay, so using that, and W was exactly that weight, right? So W was exactly this weight, correct? So what should the answer be here? So what are B prime and C prime doing? They're running the efficient measurement, right?
1 by q minus 2 delta.
Yeah, okay. So 1 by q minus 2 delta. Is that okay? Because we want B prime and C prime to so we want B prime and C prime to be efficient because B prime and C prime are implicitly going to use queries to the oracle, right? And if it's inefficient, they can make exponentially many queries, which we are not allowing. So it's important that they're efficient, which means they make only poly many queries. That's why we had to use this efficient measurement here. Otherwise, we could have directly used this, which is not okay because you need exponentially many measurements. Okay, and so, but then you have to pay a small price. So that's why we chose the parameters like we did. So you have a small price, but you're guaranteed that both of these would output 1. And if they do, then, if W is large, then this event happens with non-negligible probability. That's the key point. Okay, so that's the first note. The second note is, if both outcomes are indeed 1, as in these two, right? You make the efficient measurements, both of them give you 1. Okay. Then the leftover state is, so what was the statement of the theorem? The second point in the theorem? Okay, so this is recall theorem 4 point, what is it? 1 point, wait, which theorem was it? 2.8. 2.8.2. So point 2 was saying that the post measurement state after getting 1 1 is 4 delta close to what was this 4 delta close to? You have it in your notes, right? No? Second point for theorem 2.8. We wrote 2.7 or 2.6. So the statement was that it's close to span psi I, psi j to ij, such that the eigenvalue is gamma 1 minus 2 epsilon, lambda j2 is greater than gamma 2 minus 2 epsilon. We want the symmetric version of this, okay? So this is just saying for one side, we're looking at the symmetric version. Okay, so now it's saying if both outcomes are 1, then the leftover state is going to be what? It's going to be similar, right? It's going to be in the span of the corresponding eigenvalues, but with being bounded away from half plus whatever, right? Okay, so in our case, what this would mean is that the state is I such that lambda I minus half is greater than 1 by 4p, and j is such that mu j minus half is greater than 1 by 4p beta ij phi I tensor psi j. So this is on B and C. Okay. Good. So we have this. I think this is the part where the paper makes a small mistake, but that's okay. Yes, I'll erase B prime and C prime because we know what they're doing now. And then the last step is that when B does not query, SS prime, probability that it succeeds is exactly half. So B in the original game, right? The probability of guessing is exactly half because it doesn't query SS prime at all. So there's no way it would know whether which case it's in. Okay. And so thus by theorem 2.1, theorem 2.1 remember was the one about searching and wait, right? It was saying that if you don't query, so if an algorithm queries a certain set with at most some probability and you change the oracle, then the result can change with at most a certain probability. Remember that theorem? So it was a very general theorem from before. So from this one can conclude that the query weight of B on SS prime is at least 1 by 4p square t minus negligible. Okay, because so we're trying to find yeah, maybe one can do it properly. Maybe you can actually think about it a bit yourself. It's not that difficult. All you're doing is you're saying that the trace distance between running B directly and running so if you ran B in a way that does not query SS prime, okay, your probability of success is at most half. But in this, when you run B, right, your probability of success by the fact that you're bounded away from half is going to be at least 1 by 4p. Okay, this statement is not quite correct, but we'll come to it. But it would be 1 by 4p. Okay, so that means that whatever B is doing in the two cases, right, if the outcomes are so different, it must mean that it is querying the oracle. So imagine one case in which you've just removed all queries to SS prime, right? You changed the oracle entirely. So then the success probability is going to be at most half. And the other case is where it's actually the correct oracle and it's winning with a certain probability. Okay, so it has to have queried on that location from the theorem. Otherwise, the outputs of the oracles would. I can just write the theorem. It's probably easier. Let's see. Okay, so let's write the theorem. I think I'm just confusing you with hand waving. It's easier. You can see the theorem, right? So the theorem is saying what? The theorem is saying that so if you have an oracle, right? If you have an adversary A, right, that accesses an oracle H. So this is the adversary. This is the oracle. Okay, and somehow we had that. So you define some subset F, okay, and then you defined and you know that on this subset the query weight is small. Okay, so this is a subset. Yes, I didn't look at it very quantitatively. Maybe there's an let's look at it quantitatively then. Okay, so the query weight is at most epsilon square by t. Okay, and then instead of h you use h prime, which is which is different at f. Okay, so it's the same but it just changes at f. Okay, and so instead of using the original h, you use h prime. Then the trace distance between phi finally, which uses the original one, versus phi prime, which uses the modified one, the modified oracle. Okay, so this is going to be at most epsilon by 2. Right, so that was the statement of the theorem. Okay, now my pages are getting mixed up. Shoot. Okay, and now what we are saying is the following, right? So we are saying that, so suppose you had B which had access to a different oracle, okay, such that on SS prime it doesn't actually ever query. Okay, so if it doesn't query, so suppose phi prime is the one, this one, right, that doesn't ever query, then the trace distance between them is actually quite large, right, because one of them is going to win with that exactly half, the other one is winning with bounded away from half, right, so it's half 1 plus 1 by 4p. Okay, so the difference is 1 by 4p in the success probability. We're doing the contrapositive, right, so we are saying that, so if the trace distance is, come on, so we're saying if the trace distance is large, right, it implies that the query weight is at least whatever epsilon square by t, right. So now we've established that the weight is, if you use phi prime which never queries, then this would be at least whatever epsilon by 2. So epsilon by 2 over here is what, p by 1 by 4p, right, so you'll have 1 by 4p here, and if this is at least 1 by 4p, then it has to be the case that it is querying at the location where we changed the oracle, which is SS prime exactly. It has to be querying there with at least this much probability. Okay, and so you get this.
It should be greater than, right? Instead of greater than equal to.
Oh yeah, I mean that's okay. These are. Is this okay? So that's really the last step that says that. Okay, and if you're querying with non-negligible weight, then if you randomly stop the algorithm and check the query, you will be able to figure where SS prime, because you'll know the set f. Okay. So yeah, I think the remaining part is just explaining this, and so then the consequence is just to complete the argument. So the consequence is that A prime, B prime, C prime outputs. Oh, and of course this is simultaneous, right? Because it's also the case that from the state, right? So we know that conditioned on 1 1, they will both output with that probability. Okay, so the probability that you would get SS prime from this is going to be, so this, it will output it with probability at least eta, because we conditioned on the event that you output, or sorry, that this query weight was 1 by q, and that happened with probability eta, which was non-negligible. So it's eta by q p to the 4 t square, whatever. Anyway, all of these are, this 1 by t square is coming because you're like the whole thing is squared because you want both events to happen, and you're getting a 1 by t because you're measuring one query, right, from this that you're going to see it at once. Okay, so that's the, okay, and this is which is non-negligible. Okay, so this actually shows you that you can extract. The problem, however, here is that this is just saying that you're either going to be, you only have weight on lambdas which are either, which are bounded away from half. Okay, but it could still be that on an average your result is half, right? Like you could have, for example, you could have, like, say you get 0 with half probability and 1 with half probability. So on an average you'd still get half. Okay, so this argument is not quite, I think there's a small error in the argument. Like you shouldn't do, like, the symmetric version needs to be done more carefully. You have to do, I think, one side first and then the other side. I don't think you can combine them, because if you combine them then you can't get this statement, right, that the trace distance will not be different, because it could very well be that this thing is also outputting with probability half, succeeding with probability half. Maybe I'm wrong, but this is something to check.
Can you repeat the issue? I didn't get what the issue.
So the issue was that we were concluding that phi t wins with probability at least 1 by 4p, right? That's what we were saying. But the point is that this statement is just saying that the eigenvalues are bounded away from half.
Right.
But it could be that the weight beta is such that once the eigenvalue is 1, so with half probability, so it assigns half weight on eigenvalues 1 and half weight on eigenvalue 0. Both are bounded away from half, but on an average your winning probability would be half. Okay. So I think that's where this proof is a little bit wrong. I'm not sure, I could be wrong, but this is the part which I've felt is not quite correct. So if you had something like this, right, if you had minus half is greater than 1 by 4p, then you could unequivocally say that you're winning with at least 1 by 4p, or the other way. So you can do it separately, maybe the argument, and then you can combine it, but I think a little bit more work is needed to complete the argument from what I can tell. But okay, nonetheless you understand the idea, right? So we've shown that you can extract it, and then the remaining things we'd already put in place. Yeah? Okay, congratulations. You now know how to construct unclonable encryption in the random oracle model. So the homework assignment is to do it in the plain model, okay? Right, so we have this sorted. So today we're going to start with a new topic, and it's going to, at least the beginning would require a lot of algebra. So that may be good news for some of us, or may not be good news for some of us, but we'll see. Okay. So this one is basically about pseudo-random states. So basically it's about building cryptography using weaker assumptions than one-way functions. And it turns out that when you're quantum, you can do a lot of things, and there's been like a lot of development in this area in the past few years, and I've been very jealous and got left out, so I'll at least tell you what has been done, like the two key results. Today, however, we are only going to be able to likely cover the preliminaries. Maybe that'll take one more lecture, I don't know. So that's the outline. So I'm going to teach you from some lecture notes by Andrea, and I realized that he skips a lot of the proofs because he's smart, he can afford to do it, and I actually don't understand the proofs myself. So what we're going to do is I'm going to do the first lecture that he does. There's some preliminaries that he sort of assumes, so we'll not worry too much when we're doing this. We'll do the preliminaries right after. So there's a review paper on Haar measure and all these things that are going to be used. So we'll do that right after this. So if something about Haar measure is not clear, don't worry, we'll resolve it all. But the proof was fine, right? Like you got, it makes sense. Yeah, I should have asked before starting to erase, but. Yeah, but I think it would be nice to actually make sure that that part that I was saying, whether or not it's actually correct, and to fix it. It could be like a small project. For anyone who's interested. Okay, so let's start. So this is quantum pseudo-randomness, or randomness and pseudo-randomness. Okay, so these are basically essentially notes by Andrea Colledangelo. Oh man, I forget the spelling of his name. Colledangelo. Is this correct? Okay, okay. Right. So let's start with the introduction. Okay, so there's been a lot of interest in it's going to be a little bit of story writing, okay? So in the beginning, so there's been a lot of interest in random and pseudo-random states. There's also the pseudo-random unitary stuff. Excuse me. I thought it was temporary, but there's also the pseudo-random unitary things that we look at, hopefully, at least in the seminar that we're watching. But it essentially started with this pseudo-random state stuff, okay? And this is part of a broader trend, like I mentioned. Okay. So what is the trend? So basically, you're considering inherently quantum primitives. Quantum primitives. So what does that mean? Okay, so it basically means that the security is based on hardness of problems, that are that have quantum input and or output. Okay, so that's sort of the key distinction of what a quantum primitive is. Okay. Okay, and then such primitives are interesting, right? Because one, they're qualitatively weaker than one-way functions. So they are qualitatively weaker one-way functions, and yet still useful for crypto. Okay, and this is basically trying to answer the minimal assumptions program. Okay. And the second one is connections to physics. So this part I'm not really going to focus on here. There's lots of very interesting things that I also want to learn, but okay. So basically the idea is that, like Fermi was also saying, so some of the most important tasks in quantum info and in physics in general, if not most, many are inherently quantum. Okay, so in quantum information, specifically, he's saying that a lot of the tasks are inherently quantum, and you want to understand what are the physically relevant, or in this case computationally relevant consequences. So what are computationally relevant consequences? Computationally efficient, let's say, consequences. Okay, so like for example, what Fermi was saying, right, that you have black holes and these things may be best modeled by random processes, but then in nature you expect that everything is efficient, right? So can there be like some efficient description that can suffice in that case? Okay. So here we're going to focus on the crypto part. Okay. So let's look at the classical crypto landscape very quickly. This is very simplified. Okay, these are like a cartoon picture thing. Okay, so there's something called mini-crypt. So we'll not be very formal here, but mini-crypt normally has what are called one-way functions, right? So this we already saw in what we were doing, and we also know, right, that you can use one-way functions. Like these are all equivalent, right? We maybe didn't prove it in class, but we kind of had some reading assignments. So pseudorandom generators, pseudorandom functions, and this we haven't actually covered, but turns out that you can also build commitments from one-way functions. Okay, commitments are it was in one of your assignments early on, right? So we have some handle on this, and of course you can do private key encryption, right? So this we already used many times. Okay, now cryptomania is basically where you have all kinds of crypto. So you assume that you can do public key encryption. So whatever assumptions you need to do public key encryption, and you can also do oblivious transfer. So these are essentially more or less equivalent things. So oblivious transfer, have we discussed this before? Not. We haven't. So okay, so oblivious transfer, very simply, maybe I can quickly say, is that there's Alice and Bob. Bob holds, okay, so Alice has say R0, R1, okay, and Bob has a bit B, okay, and we want some sort of a protocol such that at the end of it, Bob learns RB, okay, and Alice does not learn anything. Okay, it's kind of a very weird thing because you can do one thing, like Alice can send R0, R1 to Bob, okay, and Bob can obviously learn RB from this. Alice doesn't learn anything about B, right? But Bob also learns R not B, right? He also learns the other. Conversely, you could send B to Alice, right? And then Alice can send just one of them, R sub B, but then Alice learns B, okay? So the cryptographic magic is that somehow Alice doesn't learn B, and yet Bob only learns one of the bits. Okay, so this is oblivious transfer. There are many variants of it depending on how B is chosen and who chooses B, but that's the idea. Okay, so this is oblivious transfer. So when you're doing public key, so for example, we don't know how to build oblivious transfer, so we don't know how to build such an object from these kinds of assumptions. Okay, so that's the difficult part, and it turns out quantumly you can. Okay, so that's one of the fundamental results. Okay, so you have oblivious transfer, then you have multi-party computation, MPCs. So what is a multi-party computation? So multi-party computation is the following. So Alice has some input X, Bob has some input Y, okay, and say Alice wants to compute some function which depends on x, y. Bob wants to compute some function that depends also on x, y, but they should not learn anything more than what they could learn from the output of the function. Okay, so in particular, it could be that f a is just outputting perp, and f b could be outputting r sub b. Okay, and you don't want them to learn anything beyond the function.
Could you please repeat this?
Yeah. So here the problem is the following: Alice has some input x, okay, Bob has some input y, and Alice wants to learn some function of the inputs of both Alice and Bob. Similarly, Bob wants to learn some function of the input f sub b of both Alice and Bob. And what we want to make sure is that Alice does not learn anything more than the output of f a. Okay, so this is in quotes, right? You have to formalize what it means. And similarly, Bob only wants to should only learn f b of x y, nothing more than this. Okay, And I was saying that, okay, to see that this is actually non-trivial, you can just look at oblivious transfer, right, as an example, because in oblivious transfer, f sub a is output perp regardless, okay, and f sub b is output r sub b, okay, and it's not clear how you would implement it, right? It's a very interesting thing, but this is obviously much more general, right? So this is called multi-party computation. So you can evaluate whatever function you want depending on everyone's input, without leaking anything more than the output of the function itself. Okay, and it turns out that if you can do OT, you can construct multi-party computation classically. So this primitive is somehow universal for building MPC. Okay, so these are more advanced topics in classical crypto. Okay, and this also allows you to do key exchange, right? Because here you're assuming that everyone has access to the same shared key. And this allows you to do key exchange. Of course, public key encryption allows you to do key exchange. So it's already. Okay, so these are some of the nice. So that's sort of the landscape of classical crypto. So now let's look at quantum crypto. So it's conveniently we have some space here. We have time. What? Okay. Okay. So quantum crypto landscape is the following. So you have. So this thing doesn't exist already, right, in the classical world, because besides the one-time pad, you have shared secrets and you do one-time pad. Other than that, we don't have anything unconditional in the classical world, right? That essentially. So here you have QKD, of course, right? So that allows you to do key exchange. It sort of assumes authentication, but authentication in the sense that you know who you're talking to, but beyond that it allows you to exchange keys, right? Then there's mini crypt, mini q crypt, let's say. Okay, so here you have one-way functions plus quantum communication. Okay, so that's how we are thinking of what we mean by mini q crypt. So here you had one-way functions in classical communication. Here you have one-way functions plus quantum communication, and you're trying to see what are the consequences. And it turns out that you can actually do oblivious transfer here. Okay, so just assuming one-way functions, if you have only classical communication, we don't know how to do oblivious transfer. But in the quantum world, if you have oblivious transfer, if you have one-way function and quantum communication, you can do oblivious transfer, and consequently also multi-party computations. Okay, so this is sort of a very surprising thing, which was actually Andrea was involved in the proof of one of these things. Okay, and then there's also this notion of quantum public key encryption. So yeah, we'll not get into this, but you can have a notion of public key encryption just from one-way functions as well, if you allow quantum communication. Okay, it's not as useful obviously because you have to use like a quantum message as a public key, which is not the best thing, but or not the most reliable thing to use, but nonetheless. Okay, and now we're looking at this little world in between this unconditional and mini q crypt. So an set of assumptions which are potentially weaker than one-way functions. And this world is now called microcrypt, or probably could be called micro-q-crypt, I don't know actually, but there's no classical analog, so okay. And here some of the building blocks include pseudorandom states. Okay. Pseudorandom states. So there are lots of objects here that we'll probably not get into yet. Okay. So there are also some things called EFI pairs and so on, and other inherently quantum primitives. Okay. And the relationships among them is still an active area of research. So we know a good amount about, like we have good indication on what is the weakest, but we don't have proper separations among all of them. By separations, I always mean oracle separations, because obviously if you manage to separate anything, you separate P from NP, and this is not something we, although actually it's not very clear whether for quantum input output it's the case. Yeah, but maybe you separate some quantum classes. Okay, I have to check that. Okay, I'll look into this. But the main interesting thing here is that there is an oracle separation between a pseudo-random state and a one-way function. Okay, so that's why we believe that this is potentially weaker than one-way functions. And interestingly enough, even just assuming a pseudo-random state, one can build commitments. Okay, and quantumly, if you can do commitments, you can also do oblivious transfer. And if you can do oblivious transfer, you can also do multi-party computation. Okay, so this is very surprising as well. Is everything okay? Any questions?
We don't even need many crypts for NPC.
Yeah. You can do something even weaker. I mean, you can assume something even weaker and then build commitments. Okay, so the main goal of this series is going to be to basically construct from pseudo-random states commitments. So we'll see how to do that, and we'll try to show a separation between pseudo-random states and one-way functions, an oracle separation. Okay, those are the two things that we really want to cover. Okay. Like I said, that was the outline. So section 2 is now going to be defining random and pseudo-random states. Okay, section 3 is going to be to define PRS, or sorry, to show that PRS imply commitments. Okay, and this is separately known that commitments plus quantum communication imply oblivious transfer, which implies MPC. Okay, so this part we'll not likely cover. We'll just show how to construct commitments from pseudo-random states. And finally, we're going to show how to use pseudo-random states to establish pseudo-random states are weaker formally than one-way functions. Okay. So today mostly we'll focus on this one. These two are probably going to take a little bit longer to do. Okay. So let's get right to it. So defining random and pseudo-random. Okay, so here we're going to look at two things. Okay, so that's the story. So we're going to look at the Haar measure. So this one is a very quick overview, so we're not going to prove anything in this section, but we will do a proper tutorial on Haar measure either today or next. Oh, there is time. Good. It's barely been a half hour. Okay, and the symmetric subspace. Okay, and then the other one is the definition of a pseudo-random state itself. Okay, so let's start. So let's start with this one, right? Haar measure and the symmetric subspace. So informally, this we have kind of already discussed a bit, but let's just write it. So a Haar measure is basically a uniform measure over quantum states or unitary. Okay, and similarly a symmetric subspace informally is just a set of states that are invariant under permuting the registers. Okay.
only be all states.
Should that? I think he's considering pure states here. Yeah, let's see how he defines it. Maybe actually I don't remember. Yeah, we'll probably see in the tutorial.
The first statement is true for pure state. The Haar measure thing.
Yeah. You're saying that Haar measure is only defined over pure states, not over density matrices somehow. Okay. Yeah, so, but I think here also he's referring to pure states, but we'll see, or maybe not actually. I don't know. We'll see. Let's see what he's trying to prove. Okay, and then the claim is that they are related. Okay, so that's the fun part. Okay, so let Sn be the symmetric group over n elements. Okay. So let pi be in Sn and d be some natural number. Okay. Okay, good. And then we're going to define p sub d pi as follows. So you go from I1 to ID. So this notation is just 1 to D, right? Because you have also IN, yeah, in registers. Okay, and you're sending pi inverse 1, I pi inverse n, I1 to IN, right? So basically, you take your input register and you're permuting it with pi. Okay, so you're doing it for every basis element. Okay, good. Okay, so basically p d pi acts on CD tensor n and permutes the n registers according to pi. Right? I have no idea. I was also thinking this. I'm not sure. Maybe it's some kind of convention. Do you know why it is pi?
What?
Why they use pi inverse instead of pi? I guess you could write it the other way, but like you write I1 to IN and then I pi 1 to. That won't change anything, but I'm not sure why this specific convention.
It's just convention. I think one is going to pi inverse.
I1 is going to I pi inverse 1, right? Yeah, I don't know. I don't have a good answer.
No, it's just a convention. So if you see, so it acts on 1 to n, right? So you can see that what it is doing. It should be implementing permutation on 1 to n. If you write pi, then it will input pi inverse on that.
Well, let's see. Suppose I have, say I have, say 1, 2. Okay, I want it transformed. So I want index. So let's call this index 1, index 2. Let's call this, I don't know, 7 and 8.
Or in fact, consider PD pi 1 into pi 2. Then this inverse will make sense.
PD pi 1 into pi 2.
So instead of one permutation, you have 2.
Okay. Oh, which way do you want to compose?
How about that?
Okay, let's sort it separately. Let's not waste everyone's time. Sorry. I don't know, but yeah, maybe you can tell me later, and then next time I can quickly tell them if there's.
Yeah, there's a lecture note by Aram Haar also there. I can.
I see. Yeah. Maybe you can tell me.
Properties.
Right. Yeah, there must be some good reason. I don't think they just put pi inverse for no reason, but.
There's a paper called Church of. Sorry.
Subspace, no.
Some-
Church of Hilbert space or something. Yeah. Anyway, okay. Yeah. So that. Yeah, so I'm going to look it up and tell you next time. Okay, so now the definition is for the symmetric subspace, right? So we've given the definition of PD. So using this, we can define the symmetric subspace of, yeah, so he is in fact defining a subspace of a vector space, like of CD tensor n. So I guess it's indeed looking at pure states. Okay, so this is defined as symmetric d comma n psi in CD tensor n, such that, what do you think it should be?
Like some sort of invariance in the PD phi for all phi.
Yeah. What should it be?
So PD phi should be an element of sim D.
Yeah, so the way they're defining it is that, psi is sent to itself for all pi. So regardless of how you permute the registers, the state is the same, right? So that's the definition. Okay. So some notes, right? So this is indeed a subspace, right? So this you can check because if you have two elements, so for all psi 1, psi 2, in the symmetric space d comma n, right? It's sort of obvious that alpha 0 psi or whatever alpha 1 psi 1 plus alpha 2 psi 2 is also in the same subspace, right? It's just by linearity of the transformation, right? Okay. So now definition. So now we're defining this object called pi symmetric d comma n. So we had p sub d, which was taking in this pi, an element of the symmetric group. Now we're defining this pi sim superscript dn, okay, as so this is the orthogonal projection onto the symmetric subspace. Okay, so basically just projecting onto the space. Then what's the theorem? So now here's an interesting theorem. So it says this projector you can write in terms of PDs. How can you write it? So this gives you like all possible permutations, right? And you sum over all possible permutations. Okay. So you project on all possible permutations. You apply all possible permutations, and that is essentially a projection onto the symmetric subspace. Okay. So we'll do the proof a little bit later, but you can also kind of check, right? To show that it's a projection, you have to show like basically pi sim square is pi sim, right? So that's just a little bit of math. You can actually do it, and then you can clearly see that it's a subset. The image of pi sim is going to be inside the symmetric dn, right? And so on. So there's like relatively simple steps, and you can sort of establish that it's going to work. And also that anything which is in the symmetric subspace will not be annihilated by sim, and so on. So basically those three steps you can combine and you'll get the answer. We'll do it more carefully. Okay. Alrighty, and now, nice. So we let d be natural number, okay, then the Haar measure mu sub d is the unique invariant measure over the unitary group. Okay, so what that means is that for any integrable function f that goes from the unitary group to some v, and for any u tilde in the unitary group. Okay, I'm going to use a slightly different convention when I'm using the other paper, because it's hard to stay consistent when you're looking at different papers, but for now this is fine. So it holds that it's basically left-right invariant. So what that means is that u acting on ud mu d u fu du is the same as, you do the same integral. So I'll not write this u every time, okay, it's the same thing. Mu d u acting on f u tilde dot u du, okay, is the same, and it's the same u mu t u f acting on u times u tilde d. Okay, so what it's saying is that you can pick any element in the unitary group, okay, as long as you're integrating over the Haar measure, you can offset the function by some u tilde by either applying it on the left or on the right. The integral would be the same. Okay, so basically it's not giving any partial treatment to any specific unitary, so they're all going to get essentially be treated the same. Okay, so that's the intuition. So let's write this. Okay, so far it's very easy stuff. There's nothing very deep. Okay, so now
What's V? F must be unity to V.
oh, it's some set.
Any arbitrary?
There may be some restriction that it has to be integrable. Like normally we'll think of this as some, it can either be a matrix or a real number, something like this is what we'll use. But I don't think I'll look at the formal statement next time, because these are lecture notes, so it's okay, let me actually give you the precise statement. Since you asked, let's see. Yeah, it just says an integrable function. So I think an integrable function can, like, whatever codomain you can have for an integrable function, I think that's fine. There's no other restriction than the fact that it has to be integrable. Yeah, because even in the formal notes, it doesn't specify what the codomain is. Okay. Any other questions? All good? Okay. So where were we? Yeah. So okay. So the Haar measure doesn't prefer any direction or basis, right? That's sort of the intuition, right? So you can move things around, nothing will change. I can arbitrarily do that. So it treats them equally. It's very democratic. Oh, well, not quite democratic, but okay, it doesn't matter. Okay, and so far, we spoke of Haar measure for unitary groups, right? Haar measure for unitary groups. for the unitary group, right? What about states, right? Haar random states. Okay, so for that we'll need some more notation. So let's introduce the notation. So I'm going to use expectation mu t. Okay, so this is, I'm using this arrow like thing to basically say what it means. So we're basically going to use an integral here, and whatever quantity I have will go here. Okay, so this is over ut. Okay, so because it's a measure, right, so we can think of it as an expectation value, so there's nothing very deep happening in this notation. We're going to use psi, if it's a pure state we'll write it like that, and when we say psi sampled from mu d, this is what we mean. Okay, so this will basically mean you sample a unitary according to the Haar distribution, okay, and you output psi as u acting on some fixed initial state. Okay, so 0 is like some fiduciary state or whatever. Okay, and then finally we have expectation of f on psi. Okay, and this basically we define, expectation is you get psi from mu t. Okay, so you sample a Haar random state and take expectation. What does this mean? What do you guys think it should mean?
That f will depend on u through this relation. You integrate over u.
Exactly. So we use this notation. Okay, so we'll write it as you sample a u according to the Haar distribution. Okay, you take f and you have it act on u. Right? That's just so nothing very deep. Okay, we're just using, all that it's doing is that it's taking whenever you have to do a sample a Haar random state, you basically sample a Haar random unitary and you apply it on some fixed state. So there's nothing too complicated. Okay. And an example of f, right? Maybe I should also write. So an example of f could be f acting on psi, could be quantum circuit, basically. Quantum circuit q. So you have, basically it's the probability that q acts on psi. Could be probability q acts on psi and outputs 0. Sorry, I went a bit vertical, but okay. So it's just an example of what kind of f's we would likely look at. Okay, and then q is a quantum circuit. Okay. So now, at least in the notes, Andrea says how to make sense of the Haar measure. Okay, so the first thing that he says in the notes is that one can sample psi from mu d as follows. Right, so what I described was the formal definition, right, that you're supposed to sample a unitary and then you're supposed to apply it to some fixed state. But it turns out that you can also do the following and it would give you the same distribution. He doesn't give a proof, so we'll see if we can get the proof from the notes. So you sample a string, okay, of n bits, and then you sample this quantity, basically it's a real number, okay, from the Gaussian distribution, okay, where this is the mean, and this is the variance. Okay, so you sample a random variable from the Gaussian distribution with 0 mean and 1 variance. You also do that for, oh shoot, I should put it on silent, forgot. Okay, and then you set C sub x as ax plus I bx. Okay, so it's a complex number. So you've sampled basically a random entry using the Gaussian distribution, and you've done it for every x in 0, 1, n, and then you output the normalized state C CXX, and with some normalization. Okay, and the claim is that this inefficient procedure, informal claim. Okay, so one can check that this distribution is invariant under the application of under the application of a unitary. Okay, and then he gives an argument, but I guess the point is that if it is invariant under a unitary, it's essentially the same property that we wanted, because a Haar state is also going to be invariant under unitaries.
What does it mean that for some fixed u psi equal to psi?
Yeah, the distribution over psi, it's going to be the same. Not for a fixed psi, but I think the entries of psi are going to be invariant whether you take psi directly or you do u and then you take psi.
The probability distribution of the entries. And this is true for a single unitary or?
For any arbitrary unitary, yeah. So you fix a unitary and then you check the distribution is the same. It's essentially the same statement as, like you say the Haar measure is invariant, right? It's in the same sense that you say you take any v, u, and you do fu, du, and where's the measure? How do you write the measure? Mu? Oh yeah, mu u, right? So this is the same as mu u, fu, du. I think it's in the same spirit that, and this statement is true for all v. So basically you fix a v and then you show that the distribution of psi and v psi is the same.
So what do you conclude from that? Like the relation between Haar and this?
Yeah, so I think that they're probably just trying to say that a Haar vector also satisfies that property, and I guess it's the unique vector that satisfies the property. At least for unitaries, that's true, that it's the unique measure that satisfies the property that it's invariant under a left-right multiplication. So I'm guessing something similar must be true. But like I said, this is not a proof by any means. We'll do the proper proofs and things in the later section. This is just a sort of high-level idea of what we want, but we'll fill in the gaps. Yeah, that's why I realized that, like, if I was Andrea, I could answer your question right away. But since I'm not, I'll actually have to study the thing in detail and tell you.
No, this is quite magical, right? When you're sampling from Gaussian distribution and
Yeah, and it's not clear to me why where the Gaussians are coming in. Like, what role are they playing? Because so far it doesn't look like why that distribution, right? It's not clear.
the joint distribution usually remains Gaussian, so
Under what?
like these entries,
Huh?
they are sampled independently, right?
Yeah.
And then joint distribution is some easy Gaussian distribution. If you have other distributions, then the joint distribution might not be as easy.
I see.
But this is,
When if we use uniform distribution, the joint distribution will be uniform.
yeah, but uniform seems like doesn't have any structure. I don't know. I'm guessing that normal comes in a lot of ways. Like central limit theorem will also tell you that.
Yeah, but that's when you're looking at sum of entries, right? There's no sum as such, right? So that's why I was a bit more concerned. Joint distribution is just a product, right? Because they are independently sampled. So that's true for arbitrary distribution. I don't know. Okay, let's not
Yeah, that's not there.
speculate at this point, but yeah.
Haar random unities being unique does not imply Haar random states like are unique.
Haar random unitaries does not imply Haar random states.
Like are unique.
Yeah, that's what I'm saying. There's a lot of arguments I'm missing here. I'm not. The only thing that I know for a fact is that, which also I don't know how to prove, is that at least for the unitary group, if you demand that there be a measure which satisfies this property on both sides, it turns out to be unique. Like there's only one measure that will satisfy this property. We will look at this in more detail. So that's the uniqueness part. Now whether it applies to vectors, I don't know. Yeah. Okay, but I think here he was his point. I don't think we need the proof in what we're going to do. Here I think he was just trying to say that you can actually sample it. You don't have to sample the unitary itself. So he was giving some.
Equivalent then
Yeah.
is interesting to it is interesting to see the proof.
Yeah, I agree. But for the purposes of what he's trying to show, I think he's not going to use that proof. So he probably didn't spend too much time. But yeah, I also couldn't find a.
And so why this is inefficient? What portion is inefficient?
This is exponentially many strings, right? So you have to do it for exponentially many. No, I mean at least it's an n-bit string, right? You have to go through all n-bit strings. You have to sample 2 to the n elements. Actually, twice 2 to the n. Okay. And then in practice, so by this he means in quantum info. Okay, so in QI, one typically needs to compute these kinds of quantities. So expectation f of u, okay, for functions of a certain kind. Okay, so one example is you're trying to compute this quantity. Okay, so f has this form. You have u tensor k, and then u dagger tensor k, right? So it's sort of just like some evolution, and this is some observable on CDK. Okay, so often these kinds of quantities are of interest, and we'll also look at it again. And so there are two useful facts. Okay, so for all operators O on CD tensor K, it holds that number 1, expectation u mu d u tensor K O u dagger tensor K is in the span of PD pi, where pi is in the symmetric group size K. Okay, so you take this object, you take its expectation, and this object is a matrix, right? Because you had a matrix, you multiplied it with some matrix, so you're getting a matrix, and this matrix is going to be in the span of the set of all basically spanned by the permutations. The matrix is implementing the permutation pi. Okay, so you can write them as a sum of permutations. Okay, it's very non-trivial, right? It's not obvious at all why this would be the case. So
Is it equivalent to saying that this is in the symmetric subspace?
the symmetric subspace we defined for for a vector. Here it's spanning operators, so it's a little bit different. Okay. And then, yeah, but maybe there is some extension to operators as well. I don't know. Okay, and then the second one is that the trace of expectation of unitaries from the Haar measure, so same as above, right? U dagger tensor K turns out to be the same as the trace of O. Okay. Yeah, but it seems very surprising to me, at least, because
Second part is the cyclicity and linearity of trace. The trace can go inside expectation, then
yeah, actually you're right. Yeah. So the second part is at least straightforward. Good. You're right. Thanks. Do you also see the first part somehow magically, or the first part is probably a bit more involved? Okay.
the first part is magical because O is not symmetric by itself.
Right.
If O was symmetric and the permutation, then yeah.
Right. Okay. And apparently from these two claims one can deduce the following: mu t psi tensor K. Okay. So basically it's taking, you can take O to be psi, right? So you take it to be rank 1 in this. Okay. And this expectation is going to be 1 by k factorial, right, sum over pi sk pd pi. Which also matches so why the coefficients are identical I don't actually know.
But you define with 1 over k factorial, this pi is symmetric. Pi symmetric you define with 1 over n factorial, so there should not be any division.
So how did we define pi symmetric? Let's see. Yeah, so I don't know why he's normalizing if he's just using the definition. But I guess it is already normalized. That's why we put. So I guess this thing is 1 anyway, so I don't know why he's adding it. Actually, I'm not sure if it's 1. It's a projector, so it should not be 1. Yeah, so I think here it's, wait, n and d, n and k are the same, is it? I think there's a difference. This is k, that is n. I think they're different
So
objects, right?
N was Sn, so here you take Sk, so they are on the same thing.
So what was n denoting? The symmetric group,
The
yeah.
number of indices.
Right. Yeah, so then it's not very clear to me. Yeah, so I suppose it's still okay, right? If the trace of this object, PD is a projector, right?
Yeah, but
And they're distinct projectors, I guess. So when you trace them, each will contribute to 1.
But
You'll probably
PD is
get
not
K.
rank 1, is it?
Huh?
PD is not rank 1 projector, is it?
Uh,
PD was some over all permutation.
It is,
Oh no, PD was for single
For
byte.
single byte.
yeah. So it's rank 1, right? It's just sending something to.
No,
No, that was
then
also
that
sum
is-
over all eyes. Yeah.
It's not rank one.
Yeah. So that's what happens when you don't know the full proofs. So we'll do the proofs properly next time. But
But these proofs are actually easy in the sense that you just check the symmetry in the left hand side and then use the argument that the left hand side must lie in this span and then you just compute coefficients.
yeah, so that part I'm not very familiar with. So I'll have to do the full thing and get, like, also make you guys do the full thing, unfortunately. But the point here is that yeah, so what wasn't clear to me, I don't know, do you guys see why the coefficients have to be the same already? Or whatever, proportional, doesn't matter. Like, that statement just says it's in the span, right? It doesn't say what the coefficients are. Is it immediate to you why the coefficients are the same? Oh shoot, it's time, damn it. Okay. Okay, so I guess, yeah, let's stop here. So next time I'll define what a pseudorandom state is.
So the thing
And,
is that there the O is arbitrary, right?
Yeah.
And here O analogously will be some fixed state. It should not depend on the sign, the answer. Because here I will replace psi by u get 0, right? So you will have at the end u tensor k, get 0 bra 0, u dagger tensor k.
Mm-hmm.
So this means it doesn't depend on the object O there, because the object O is fixed.
Uh-huh.
So I mean, probably one can argue like that.
Yeah. I suppose it's, yeah, I'll have to think about it. Yeah, there has to be some symmetry argument, of course, otherwise it won't work, but yeah. Anyway, so yeah, so we'll look into this next time and we'll define
So if k
pseudorandom
equal to 1,
states.
then you know the answer is identity, right?
For k equal to 1, the answer is identity.
I mean, I know from other sources that if you just integrate over arbitrary operator on single copy, then you will get answer that will be maximally mixed state actually.
Yeah, I think we'll prove all of these things. I think by the end of, like, once we go through the notes, I think these things will become more familiar, because and these are also useful elsewhere in quantum info, apparently, for a lot of learning things. It's like Weingarten calculus and all these things. I don't know. We'll sort it out. Yeah, so we'll go through everything in detail. So we'll probably spend a lecture or two on doing the Haar integration and all of this, and then once we have that in our toolbox, we'll resume. Primarily because I don't know these things. Otherwise, I could have gone a lot faster. So okay.
Okay.